Viewers, I hope that you all are well and doing well. Today we talk about Geiger-Müller counters or GM counters. Okay, let's start. If we increase the electrode potential, we pass from proportionality region to region of limited proportionality. If we further increase the supplied voltage in the order that it is 800 volt to 1000 volts, then we reach to Geiger-Müller region where Geiger counters are operated. Here resulting pulse is very much larger than proportional counter. All pulses are of same amplitude regardless of the number of original ion pairs. Let us see principle of Geiger-Müller counter. It works on the principle of ionization of gas molecules by the incident radiations. If you see the construction, Geiger-Müller counter is identical to proportional counter. It consists of a cylinder which acts as cathode. There is central stiff wire made up of tungsten which acts as anode, and thickness of this anode wire is from 0.02 to 0.05 millimeter. If we talk about diameter of this tube, it is from 0.3 to 15 centimeter, and if we talk about length of this Geiger tube, it is from 1 centimeter to 100 centimeter. Commercially available tubes are filled with 90% argon gas, which is a principal gas, and 10% ethyl alcohol or 0.1% halogen gas, which acts as quenching gas. We will later talk about what is quenching. A thin mica window of thickness of the order of 10 micrometer isolates the gas in the counter from atmosphere. Now we talk about working of Geiger-Müller tube. The charged particle entering the tube ionized gas present. Its primary ionization. Electrons are attracted to anode. Because of high potential present on the surface of anode, they gain sufficient acceleration and hence produce further ionization, which is secondary ionization. Now we see quenching, and we talk about what is quenching. Actually, the gas in the Geiger tube is immediately made non-conducting in order to count further incoming pulses, actual particles. This is called quenching of discharge. But why we need quenching? What's the problem? When positive ions reach this cathode, just before striking, the positive ion pulls an electron from there and becomes a neutral atom. Now this atom is in general in an excited state. It goes to ground state and radiations are emitted. Some of these radiations or lines fall in ultraviolet region. These radiation, when strike the surface of cathode, liberate photoelectrons. These electrons move towards anode and give rise to spurious counts. So to prevent this, we need quenching. There are two types of quenching. One is organic quenching and second is halogen quenching. First we see what's organic quenching. Typical organic quench tube has 90% argon and 10% ethyl alcohol, which is an organic gas. Positive ions collide with organic molecules. Positive ions collide with the organic molecules and pull an electron from the gas to get neutralized. Thus, the ion reaching the cathode now are only of organic gas. Now, excess energy of organic gas molecules is used in dissociation of molecule rather than to radiate energy. So, no photoelectrons are emitted. Organic quenched GM tubes are of short lifetime and are not suitable for operation in very high fields. To overcome this, the technique to halogen quenching was introduced. So we see what's halogen quenching. This involves the addition of small quantity of halogen gas such as chlorine or bromine. A typical filling is about 0.1% of chlorine gas to argon or neon gas, which is a principal gas. The quenching action is same as discussed in case of organic quenching. Now we talk about characteristics of Geiger-Müller tubes. Here we talk about dead time, recovery time and Geiger plateau. First we see what is dead time. Due to low mobility of positive ions are heavier, their drift velocity is small. So there is formation of a cloud of positive ions near the anode. There is a formation of positive cloud near the anode. This reduces the intensity of electric field to a great extent. Thus, approaching electrons do not gain sufficient energy to start new avalanches. Now, the detector is then inoperative or dead for the time required. Thus, what's dead time? Dead time is time between initial pulse and time at which a second discharge can be developed. What is recovery time? After the dead time is over, sum of electrons and positive ions recombine and form neutral atoms. During this time, when new ionizing radiations enter the tube, pulses of lower amplitude are formed, which are not counted by the counter. Thus, time taken for tube to overcome or to recover to its fully sensitive state to give the next pulse is called a recovery time. And here, from this point to this point, it is recovery time. And the sum of that time and recovery time is called resolving time. Now we talk about Geiger plateau. If we plot the count rate versus anode voltage, the voltage at which counting just starts is called threshold voltage. It depends upon gas and pressure in the tube. After a very sharp rise, if you look, after a very sharp rise, counting rate remains almost constant with increasing voltage. This flat region where counting rate remains almost constant is called the plateau or Geiger region. The length of plateau is 100 volt to 300 volt. If this region becomes shorter and steeper, then it means that Geiger tube is near the end of its useful life. GM counter operated in this region eliminates the need of costly regulated power supply. Viewers, that was all about Geiger-Müller counter. Goodbye.